I read and take notes. In the year 2000, the population of Israel was approximately 6.04 million. And by 2050, it is projected to grow to 10 million. Use the exponential growth model, A of t. And now you'll tell me if this reminds you of anything. A0 e to kt, in which t is the number of years after 2000. T, number of years after the year 2000. What does t equal for year 2000 then? Perfect. To find an exponential growth function that models the data. Let me just put it on the side, and let's see if we remember this. At some point in time, when we started chapter 4, we had something like, do you remember what this was? I know I didn't ask you to memorize it, and you don't have to. It was the continuous compound interest. The accumulated value, the principal, the annual interest rate time in years, and E is the base of the exponential function. Look at the analogy, right? So this is number of people. This was the accumulated value. This is the principal, the money we deposit at the bank, which is the initial population. So A0, initial population. When we started counting them, it doesn't mean that the entire population started in 2000, right? All of a sudden, 6 million people descended on that land. No, but that's when we started counting them. K, the same thing, but this time K, although it's like an interest rate, it's the growth rate. And T has the exact same meaning. Number of T is years. T, time in years. So this is what it's called the exponential growth model. Exponential growth model. The exponential growth model. Now, if you remember, we have to discuss one more, which is the exponential decay model, right? And this is all. So now here, let me just give you the heads up. This will be the only difference, a minus in front of K, between the exponential growth model and the decay model. And they are all the same, right? That just one, the exponential decay will have minus in front. That's it. But it will be given to you. You don't have to memorize it. Okay, so we're asked to find this model. What does that mean? A of t is the y variable or function. There is nothing I can do to it. It's a function of t. So t is the independent variable, which is the x variable. There's nothing I can do to it. So what am I missing here? E is a number. 2.718 dot, dot, dot. So what am I missing then? In order to find the entire model, I'm after what exactly? If this is clear, and this is clear, and this is clear, then what am I missing? I'm missing K, very good, which is the growth rate. What else am I missing? So if this is the function, and this is the y variable, and K and E is a number that we know, it's Euler's number, and K is one of the variables that I don't have. What else I don't have? I don't have this. So the y variable has to be in the problem. There is nothing I can do to it. The x variable has to be in the problem. E is a number. K is a quantity I don't have, and also A0, the initial population. So these are the only two variables. But you can say now, I do have the original population, which is correct. So before we plug that in, which is Perfect. You are way ahead of me. I would like to talk about the information given. And you're correct. A 0 is given to us. Perfect. But I'd like to talk about these two pieces of information. It says in 2000, 6.04, in 2050 predicted to be 10. What is this? What are we told here? What are we given here? When we are told 2000, 6.04, 2050, 10 million. What is this? We've seen this before. What are they called? If you say to someone, well, in the year 2000, I made $50,000. And let's say in the year 2010, I made $100,000. What are you really giving to the person? Two ordered pairs. You're giving two ordered pairs, correct? Okay, so let's create the first ordered pair. In the year 2000, 6.04. But I cannot use this name. This is an artificial name given to a year. I have to use exactly. So every time I'm given a relationship between two variables and I'm given the numbers, I'm given two ordered pairs. Perfect. So what is the second ordered pair that I'm given? Very good. Awesome. So this is the key to understand that these are ordered pairs. Now, I also have to remember something very important. When I am really told 0, 6.04, I am really told that A of 0 equals, when I plug in 0 in the function, what do I get? Exactly. Remember, that's very important. And now what am I told with 5010? What does this really mean for our function? Because this is what we are trying to find. We're trying to find the entire function. Exactly. In other words, when t is replaced by 0, the entire function equals 6.04. When t is replaced by 50, the entire function is 10. Okay, so let's write these two equations. Let me write the equation one more time here. And now give me two different equations, one for the first one, so we can see it, and one for the second point. What will you say? For the first point, what is this? Yes, which is, I just want to plug in the numbers now. Very good. Equals, unknown, e to k multiplied by, excellent. We'll come back to it. Good. So now the second one, please. Yes? Equals A0, I don't have it, e raised to k multiplied by, excellent. So these two equations should give me both variables. From one, I should determine the initial, and from the other, I should determine k, the exponential growth rate. Perfect. So how much is k times 0? 0. How much is e, a number that is not 0? E to 0. Very good. And that's how we get exactly what Ryan said. He said A0 equals 6.04 million. But this is how the mathematical procedure works. Is that clear? Perfect. So now I have A0. I go back to the second equation, and I write 10 equals 6.04 e to 50k. Okay, so I look at this equation, and I realize that this is what type? Perfect. But it's not entirely cleaned up. I cannot think of applying anything or bringing down the power, not yet. What do I need to do to clean this up? Exactly. I must divide both sides by 6.04. Do not divide, just write it one over the other. E to 50k. Now it's completely cleaned up, and it's ready for what? Yes. Apply log to the left-hand side and apply log to the other side. So here's how we think. Two numbers are equal. their logs must be the same. If 5 equals 5, log 5 will equal log 5. So that's how why we apply log to both sides. Two numbers are equal, their logs must be the same. So the left-hand side is natural log of 10 over 6.04, and the right-hand side, I bring 50k. Remember, it has to be a factor, but they're all factors. I don't need to put parentheses. Multiplied by natural log e. So let's write on the side again, what is natural log e? What does it equal to? Okay, what base is this? E raised to which number is e? 1. So as a refresher, log in base b of the base. B raised to which power is b? That's it. So this is a very important property of log. If you apply log in any base you want, of the base of the same number, you always get 1. Also, log in any base of 1. Let's say we don't know. B raised to which power is 1? That's it. So these are two very important properties of the log. Okay, so I'm back here. What do I do to get k? Final step, I divide both sides by 50. So that's natural log 10 divided by 604. And always with these exponential growth or exponential decay, please make sure you come up with 4 digits, 4 decimal digits. So I'm looking for my software here. Okay. So let's plug it in, and you can always easily check. So we had natural log 10 divided by 6.04, and close and divide both sides, everything by 50. And the interest rate, not the interest rate, forgive me, the growth rate is 0.0101. 0.0101. How do I check if you want to check? Yes. So I will have 10 minus 6.04 raised to, in parentheses, 50 times the previous answer. Close the parenthesis. What should I get if this is correct? 0. Correct. Because that's, oh yes, because I didn't put the base. And now I have to do it again because it will put the previous answer. Sorry, I didn't put the base. So natural log of 10 divided by 6.04, and then divide by 50. Okay, and now we have 10 minus 6.04 multiplied by e. In parentheses, it was 50 times the previous answer. Times the previous answer, close the parenthesis, and now if I don't get 0, something is wrong. So that was the population growth rate. So now we do have the entire model. Everything we know, everything we need to know about this function, it's a of t equals 6.04 e to 0.0101 t. And this is it. Now there is a part B here. In which year would the Palestinian population be 9 million? So that's part B. In which year, when, will the population reach 9 million? Oh, we were talking about 7. I'm sorry. In which year will Israel's population be 9 million? Okay, the same question. I looked at the next problem by mistake. Okay. So what am I given now, and what do I do? Exactly. I'm given a of t. 9 equals 6.04 e to 0.0101 t. Awesome. That's the answer. And now what do I do? I ask myself what type of equation it is. I'm asking myself, can I simplify it? Can I clean it up? And the answer is yes, it is exponential. It's not entirely cleaned up. So I will divide by the same steps we just performed. 0.0101t. And the same thing, we apply natural log to both sides. So natural log of 9 over 6.04 will equal 0.0101t. And we divide both sides by t, like we just did. So natural log 9 over 6.04 divided 0.0101. So I go back. And this time I have natural log 9 divided by 6.04 and divide by 0.0101. 0101 and enter. So roughly 39 years, approximately 39 years. Okay. Which means in 2039. Assuming the model still holds, we don't know that. But assuming it holds. Now I want to add part C to this. And here's my question. When will the population double? Double the original one, of course. What was the original population that we started with? 6.04 million. Okay, so the question is, when will the population double? Assuming the model is still true. So let me write the model. So A of t is 6.04. I was going to write A0 again. E to 0.0101 t. So now the question is, when will the population double? Exactly. So here's how I do it. Twice 6.04 equals 6.04 times e to 0.0101 t. Why? Why did I decide not to multiply? Because I will have to clean it up anyway. And I will have to divide by 6.04. So these two, and I divide both sides by 6.04. So I get 2 equals e 0.0101 t. Okay. This is completely cleaned up, so I'm ready now to find when the population doubles, assuming the model still holds. So natural log 2 equals 0.0101 t. And then t equals natural log 2 divided by 0.0101, which was basically k. So this is the formula for the population to double. You don't have to memorize any of that. I was just saying. So natural log 2, close the parenthesis and divide by 0.0101. So it takes roughly, approximately 69 years. Approximately 69 years. In 2069, assuming the model still holds, no catastrophe happens on the globe and in other areas. Very good. So now the same idea for the radioactive decay. Same idea, same type of model. Just there is a negative in front of the growth rate. Okay, so we're given looking at a couple of problems. It says in exercises 9 through 14 on page 529, nine through 14 is still exponential growth model. So forgive me, I'd like to move on to 15 through 18. We can come back with more problems, no problem. Okay, an artifact originally had 16 grams of carbon-14. 16 grams. when we are told originally it had, or the initial population, what will this equal to then? It's the A0, the initial amount, the initial mass. The decay model is A of t equals 16 e to negative 0.30121 t. So this is the exponential decay model. So what is the difference from the previous one? Let's take a look for a moment. So we never get scared of it, right? So look at the previous one with the exponential growth, the initial value. Same base, an exponential function with base e, which is natural exponential. A growth rate or a decay rate in time. The only difference is minus, because it decreases its mass. Here it increases the number, but here it decreases the mass. So that's why the exponent is negative. Okay, how many grams describes the amount of carbon-14 present after t years? Use the model to solve exercises 15 through 16. How many grams of carbon-14 will be present in 5,015 years? So 15 in 5,015 years. We're asked to find how many grams are still left. So initially, there was 16 grams of carbon-14. What was it? Yes? Yes, carbon-14. Okay. Now, 5,715 years later, how much is still left? What do I need to do? That's it. A of 5715. Let's plug it in the calculator. Let's also look at 16 and see how many grams of carbon-14 will be present in. So the same type of question. 16. We're asked to find A of 11,430. When we have to repeat the same operation, I strongly recommend go to y equals and put in the function in there. And make sure I have to change it all. Oops, I'm sorry, I have to change to the ask mode. Okay. So in y equals, I put in 16 and then e in parentheses negative 0.30121x and close the parentheses. This is the radioactive decay model. And then all I have to do is just directly go to second and table and put 15, and then 11,430. And the answer is in grams. We started with 16, and then 5,715 years later, we got 8.0131 grams, and the other one 4.0131 grams. Okay, now I would like to ask this question. I want to add the question. I'm going to say 16a. When will the amount be decayed to half of it? What was the original? Okay, when will it decay to half of it? Exactly. So I have, either I write 1/2 times 16 so I can simplify it, or you put 8. You'll still have to divide by 16 first, right? E to negative 0.0000121 t. It doesn't matter. If you write it like this, then you will say, gone. So the left-hand side will be natural log of 0.5 because it's 1/2, and the right-hand side will be negative 0.000121 t. And then we are back to the same formula. Natural log of 0.5, negative 0.000121. So initially, the artifact had 16 grams. I would like to know how many years it took for those 16 grams to decay to half. So I have to calculate this. Go back to natural log of 0.5. And divide by, don't forget to put parentheses around everything, negative 0.000121, close the parenthesis, and we get 5,728 years, approximately 5728 years. This is basically an introduction to what is called the half-life. So we can say, and I'm going to put that in writing, a sentence, we can say that this radioactive substance called carbon-14 has a half-life of whatever amount you start with. You don't have to start with 16, it doesn't matter. For whatever amount to make it into half, the half-life for this specific radioactive substance, what is it? 728. It depends. Other radioactive substances, they decay much faster. This one is a very slow. It has a very slow decay rate. It's what? 0.0121%. Very slow decay rate. And the half-life is 5728. Okay. Let's look at another. Let's look at 17. The half-life of the radioactive element, this is the name, krypton-91, is 10 seconds. Way faster. The half-life is denoted by H, half-life. What does this mean? That if I start with an initial number, give me any number of grams you want, or milligrams you want, or ounces, whatever you want. Give me any number. 50. What happens in 10 seconds? 25. And in 10 seconds more? 12.5. And in 10 seconds more? 6.25. And so on and so forth. That's what the decay half-life means. Good. So we know that there is a radioactive substance that decays, makes its mass, or diminishes its mass every 10 seconds to half. Okay, let's see. If 16 grams, so A0, again 16 grams, are initially present, how many grams are present after 10 seconds? You already told me. So after 10 seconds, it will be 8 grams. After 20 seconds, there will be 4 grams. After 30 seconds, there will be 2 grams. After 40 seconds, right, 1 gram. And after 50 seconds, it's going to be 0.5 grams. Okay. Final problem, unless you would like to look at more. Are you interested in paintings or skeletons? Okay, perfect. 19 on page 530. So let's read the problem. Use the exponential decay model for carbon-14 again, and they are giving us A of t equals A0 e to negative 0.000121 t. So this is the exponential decay model for carbon-14. I have the decay rate, which is this, very, very, very slow. And the initial amount doesn't matter, or we'll see in a moment what we're asked to do. I don't have the initial amount, but it doesn't matter. The exponential decay rate is this. That's the K. Okay, prehistoric cave paintings were discovered in the cave in France. The paint contained 15% of the original. Original, also called initial, whichever you prefer. So they were found recently, and they measured the amount of carbon-14 present in those paintings. And it was 15% of what they had initially. Question. Estimate the age of the paintings. Do I have the original? No, but it doesn't matter. So let's say the original is A0. It was initially many years ago. But now I can measure somehow. They have techniques of measuring the amount of carbon-14 in these paintings. And they came up with a precise amount, 15% of what they had originally. Now let's identify what this means, first of all. How do I explain, or I'm sorry, express 15% of something as a product? Exactly. So it's 0.15 of the original amount. What is the original amount? I don't have it, but I have a notation for it. What is it? Exactly. So then this piece now is this. So 0.15 times A0 equals A0 e to negative 0.00121t. And of course, it doesn't matter because I divide by it, like we just did with that 16. And everything is back to the same steps. I apply natural log on the left-hand side. Negative 0.00121t. I apply it on the right-hand side, of course, and then I get t equals natural log of 0.15, negative 0.00121. And that's how we determine how old the paintings are. So natural log 0.15, close the parenthesis and divide by negative 0.000121, close. Let's see how old they are. According to our calculations, they are 15,679 approximately. 79 years old. Any questions? Any questions? Okay, let me know if you encounter any other types of problems when you do your homework. If there is anything else that you run across, then we can always go back to more problems. Any questions?